Hello everyone. In this video, we are going to use machine learning models and predict the movie ratings. We are going to predict the IMDB ratings of a particular movie, and let's get started. So as you can see over here, we are predicting a number which is nothing but our IMDB score. So this is a regression problem, and in order to work on these models, we have to do our necessary inputs. And as you can see over here, I've imported NumPy as NP. So NumPy is nothing but it is a Python library which will help us to work with arrays. And basically NumPy stands for numeric Python. And what NumPy does is that it helps us to work with arrays, and also it has domain over matrices as well as algebra. And the next import over here is the pandas. So pandas will help us to create data structures. And not only does pandas create data structures, but it also helps us to manipulate these data structures. So let it be dropping a column or editing the column name. We do it with the help of pandas. And not only editing the column, we are basically going to read our data as well with the help of this library, which is nothing but pandas. Then the third import over here is Seaborn. So Seaborn is a Python library which will help us to visualize statistical graphs. And not only that, Seaborn is based on matplotlib library. And the next library over here is the matplotlib. So matplotlib will help us to create plots. And then we have imported warnings. So when we run our machine learning models, we are given some warnings. And when we import warnings and use the line over here, which is called as warning dots filter warnings ignore. So what this will do is that it will ignore such warnings and directly run the machine learning model. And the next import over here is the label encoder, which we have imported from sklearn.preprocessing. So what a label encoder does is that, let's say we have a data frame which has a column which contains categorical variables in them. Let's say we have a column called as color, and so this color is nothing but our categorical column. So this column has to be transformed into numeric, and that can be done with the help of label encoder. So what this library does is that it will take all the categorical columns and convert them into numeric. And then next import over here is the train test split. So we have imported this train test split from sklearn.model underscore selection. So what this really does is that, let's say we have a data frame, we can split our data into train and test. So what this import really does is that it will help us to split our data into training and testing parts, which will be used for machine learning algorithms. And it is after the this import that we divide our data into training and testing, and that's where that will be used by our linear regression models. So over here, as you can see, these imports over here are nothing but our algorithms, and we have imported a linear regression model, and we have also used the decision tree regressor over here, and then we have used the random forest regressor as well as the k nearest neighbors regressor. And in the end, we are going to use the XGBoost regressor over here. So when it comes to regression, what these models really do is that they will help us to predict a number. So let it be sales price or IMDB score in our case. So for such use cases, we use these regression models. But when it comes to classification models will predict a label, whether the output is going to be yes or no, and if a person is infected with the disease or not. So such problems, we use something called as the classification models. But for now, we are predicting a IMDB score. So for that reason, we have used these regression models over here. So starting with linear regression. So what linear regression is that it is a supervised machine learning algorithm where the predicted output is continuous and has a constant slope. For example, as I told earlier, we can predict sales or a price with these models. For now, we are using this to predict our IMDb score. And then the second import over here is the decision tree regressor. And decision trees build both regression as well as classification models. When it comes to classification model, we use something called as decision tree classifier. But for now, we have used the decision tree regressor. And what this model does is that it breaks down a data set into smaller and smaller subsets, while at the same time associated decision tree is developed. And then we have imported other model called as the random forest regressor. So when it comes to random forest regressor, a random forest is a meta estimator that fits a number of classifying decision trees on various subsamples of the dataset, and it uses averaging to improve the predictive accuracy and control overfitting. So, decision tree regressor or decision tree classifier are prone to overfitting, and that problem is not seen in a random forest regressor, and it never gives us a overfitting problem as compared to decision tree regressor. And the next import over here is the k nearest neighbors regressor. So when it comes to KNN regression, KNN regression is a non-parametric method that in an intuitive manner approximates the association between independent variables and continuous outcome by averaging the observations which are in the same neighborhood. So this is our KNN regressor over here. And then we have imported the XGBoost regressor. And XGBoost is a decision tree based ensemble machine learning algorithm that uses a gradient boosting framework. And the algorithm differentiates itself in the following ways. It is used in a wide range of applications, and even the XGBoost regressor can be used for solving regression, and we can use the XGBoost classifier to predict a classification problem as well. So the random forest regressor and the XGBoost regressor do not overfit, whereas the decision tree over here is more prone to overfitting. And again, random forest regressor also can be used for both regression and classification problems. And it provides a higher accuracy through cross validation. And when it comes to random forest classifier, random forest classifiers will handle missing values. So even though we have missing values, random forest will take care of it in both regression as well as classification problems. And all these models that we have used for our machine learning will be evaluated in order to compare which model performed well. So we know if a model has performed well or not using some evaluation metrics. So over here, you can see we have imported something called as mean squared error, and then we are going to use accuracy score, and then we are going to use R2 score as well as mean absolute error. So they are nothing but evaluation metrics which will tell if our model has performed well or not. So when it comes to mean squared error, the mean squared error uh, is an estimator of measures and it measures the average of the squares of errors. So the mean squared error is nothing but the squared errors, and then we have the accuracy score over here, which will tell us how accurate our model is. And then we have something called as R2 score over here. So when it comes to R2 score, the higher the R2 score, the better the model's performance. And the R2 score should be closer to 100. And if the R2 score for a particular model is less, then we must improve the model or feature engineer our features in order to improve the accuracy. So higher the R2 score, the better the performance of our model. And then we have something called as the mean absolute error. So when it comes to mean absolute error, it is a measure of errors between paired observations expressing the same phenomenon. And over here we are going to use the accuracy score to see how accurate our model is. So the other evaluation metric that also can be used over here is the RMSE, or the root mean squared error. And the lower the RMSE, the better the model's performance. And over here, as you can see, these are nothing but our evaluation metrics. So let us go ahead and load our data. So before we load our data, we use the pg.read_csv code over here to read our CSV file. And the data set is called as the movie metadata, which is in a form of CSV file. And then as you can see over here, we have used this code over here, which is called as the pd.set_option. And this code displays the maximum column. So let us say we have these columns over here. So what usually happens when we do not use this line is that we see three dots in between, and we are unable to see the total number of columns present in our data frame. So in order to see all the columns, what we do is that we use this line of code over here, and this line of code displays all the columns present in our data frame. And as you can see over here, we have loaded our data set. So we basically stored our data in the DF, and this is how our DF looks like. So we have columns like color, director name, number of critic for reviews, duration, and such other columns. But in the end, as you can see, we have a column called as the IMDB score. As you can see here, this is our dependent variable, and this is also called as our target variable or target column. So it is this column that we are supposed to predict, and these are all the independent features. We have the movie link, we have the language and the country of origin of that particular movie, and these are all the movie titles Avatar and all these movies. And let us go ahead and do some. And in order to understand data, the first code that we use is the df.shape. So what this code does is that when we use df.shape, this code will display us the total number of rows and columns present in our data frame. So as you can see over here, using the df.shape, we see that there are 5043 rows and 28 columns. These are the total number of rows and columns present in our data frame. And then the next import that we have, the next code that we have used for data understanding is the dataframe.info. So using the df.info, we can check two things over here. One is the presence of null values in that particular row, and we find that by matching these two numbers over here. So as we know, there are total 5043 entries, and out of that you can see that in the color column we only see that we have 5024 uh, rows over here. That means that we can see that there is a mismatch over here, and it means that in this particular color column there are some missing values. Okay, and again the same thing can be seen over here as well. In the column director name, again there is a mismatch. So this value minus this value is the total number of missing data in that particular column. And again, as you can see over here in the column number critic for reviews, again we have a value called we have a value which is 4993, whereas the total entries in that particular data frame are 5043. So this value minus this value will give us the total number of missing values in that particular column. And the other thing that this df.info shows us is the type of data present in that particular column. So as you can see here, we have a column which is the color. So this color is of object type. As you can see over here, it is of object type. And then we have director name again, which is nothing but object type. But when you can see over here, the third column over here is the number critic for reviews, which is float type. And as you can see over here, the number critic for reviews shows us that all the values present in that particular column are of float type. And that's the two things that can be understood from using df.info. And then there is another way to find out the total number of missing values present in the data frame, and that is called as df.isnal.sum. So this code will display the total number of missing values present in that data. As you can see over here, in the column color, we have 19 missing values, and in the column director name, we have 104 missing values. So using the df.isnal.sum, you can see the total number of missing values in that data frame. And wherever you see a zero, that means that there is no missing value in that particular column. So the movie title, number voted users, and cast total Facebook likes have zero values in them, which means that there are no null values in that particular column. And over here, we have displayed the column names using df.columns. So what this code will do is that it will display all the column names in that particular data frame. So as you have seen over here, we have color, director name, number of critics for reviews, and all these column names. And the next code over here is the value underscore counts. So in order to see all the elements present in a particular column, we can use the code called as value underscore counts. So let us take a column called as color and use value underscore counts on it. And as you can see over here, these are the total number of values present in that particular column. So we have color, uh, we have 4,815 color uh, objects in that particular column, and then the remaining 209 are black and white. So these are the values present in our data frames column color. And the next thing you can see over here, we have used df.describe. So what this describe function does is that it will check the minimum values, the maximum values, as well as the mean and standard deviation of that particular data frames column. So it only works for numerical type data. And as you can see, we have a column called as number of critic for reviews. We do not have the color column, the director name column, because they are of object type. And as you can see over here, this describe function shows us the minimum value present in that particular column. So in the number of critic for reviews, the minimum value is 1, and the maximum value that can be found in this particular column is 813. And over here in the duration column, we have 7 as the minimum value and 511 as the maximum value. So this shows us the minimum, maximum, and over here we can see it has also shown us the mean and standard deviation. These are the 25%, 50, 75%, and this is the max value. Then we have used another function called as the df.nunique. So the nunique, what it does is that it will display as the total number of variables present in that data frames column. So as we saw earlier that in this column name color, we had two values present in it. One was the color and the other was the black and white. And that's the reason why we can see that there are only two types of values present in that particular column. And as we can see over here in this column director name, there are around 2,398 different values present in that particular column. And this is what the df.nunique shows us. It displays the total number of variables present in the data frames columns. And over here we have seen what kind of languages are present in the language column using the value underscore counts again. Previously we used it on the color column, and now we have used it on the language. And as you can see here, there are 4,704 English languages. So most of the movies are in the English language, followed by French. Then we have Spanish, and then followed by Hindi. And the least we have a language which is Filipino. There's only one movie present in the data frame which belongs to the Filipino language. And the next thing that we can see over here is we have displayed the movie titles over here. So this shows us the movie titles. As you can see, we have Avatar and then we have Pirates of Caribbean. And then in order to see what kind of Hindi movies or Bollywood movies present in the data frame, we have done something where we have taken the movie title of data frame where language is equal to Hindi. So this code will print us the name of Hindi movies present in that data set. So basically we have displayed all the Bollywood movies, and as you can see these are all the Bollywood movies present in that data frame. And the next thing that we have done over here is that we have created a data frame wherever the language is Hindi. And as you can see, this is the data frame. We have stored this data frame in BW. We save the Hindi movies into a separate data frame, and we will perform some analysis on this particular data frame. And this is the resulting data frame. It includes the color, director name, and all the columns are present in this particular data frame. The only difference is that this data frame is a subset of the previous data frame, and the previous data frame had all the languages included in it, but in this data frame we have only selected the Hindi movies over here, or the Bollywood movies, and we'll perform some analysis on it. And what we have done in this piece of code is that we have given a threshold value where we have displayed the movie names, where we have displayed the title of the movie wherever the IMDb score is greater than 7. So we have saved the IMDb score greater than 7 or greater than equal to 7 in the scores, and then we have selected the movie titles where the IMDb score is again greater than equal to 7, and we stored it in the name. And then we have selected the genre of the movie where the IMDb score is greater than equal to 7. And then we have concatenated all these values, the scores, name, and genre, and we have saved it into the Bollywood movie ratings. And as you can see over here, the resulting data frame is actually a subset of the original data frame, where the original data frame had movies which belong to different languages as well as which belong to different country. And but over here, this movies only belong to India, and the languages are in Hindi. As you can see over, the highest IMDb score for these movie is 8.5, which belongs to a movie title called as Airlift. And these are the genres over here. And as you can see over here, if a movie has action, drama, history, thriller, and war, and as again, if you see wherever we have action, drama, as well as thriller, war, we have higher IMDb score. Again, it can be seen here that we have drama, history, and comedy over here. So such genres have given us a higher IMDb score. And as seen above, uh, Indian movies have a higher IMDb score if it has a genre with action, drama, history, thriller, and war included in it. Now let us go ahead and visualize our data. So over here we have used a pair plot. So pair plot will show us all these scatter plots of our data, and the x-axis is mentioned at the bottom of the plot. And as you can see here, these are the number critic for reviews, and this is on the x-axis, and on the y we have the movie Facebook likes. And when it comes to these plots, again the x-axis over here is going to be the same, which is nothing but the number critic for reviews, and on the y-axis we have the aspect ratio. And let us take another plot to get a clear picture over here. So when it comes to this plot, you can see that the x-axis over here is the number of voted users. The y-axis remains same in this entire row, which is nothing but the movie Facebook likes. So this is how our scatter plot looks like for this data frame. And over here we have used a pie chart. And what this pie chart shows us is that it shows us the total number of distribution of the ratings And as you can see here, the rating, which is 6.7, this is nothing but the IMDb score, has 11.74 percentage throughout the entire data frame. So over here you can see this is the fixed size. Okay, and then we have given a title over here, which is called as the IMDb score distribution. And then you must notice we have used explode, and we have given values like 0.05, 0.05, and this repeats for 10 times. So what this thing does is that if we give a value called as 1 in the end, then the lowest value is going to separate from this pie chart and move 2 3 steps away from the pie chart. So when we use 1, this piece moves ahead and separates from the pie chart. So this is what explode does. And then we have used value underscore counts on the IMDb score. So this will display the count of the IMDb scores throughout the data frame. And we have only used 10 scores over here. So we have used the head to find the top 10 counts of IMDb scores, and around 11.74% of the data has a IMDb score which is 6.7. And then the next visualization over here, we can see that we have plotted the distribution of IMDb score, and as you can see, the most of the IMDb scores are between 6 and 7. And the next, yeah, again the same thing. We have given a figure size, and then we have used a distribution plot, and we have selected the IMDb score column from the entire data frame. We have selected the IMDb score, and this is how the distribution plot looks like. And then over here we have used a bar plot, and a dark grid over here specifies the background color over here. And then we have used the language column of our data frame in order to see which language of movie are repeating in the data frame. As we saw earlier, we had English language, which was highly repeating, followed by French, Spanish, and then on the fourth place we have Hindi, and in the end we have Danish. So this will display the count of languages present in the data frame. And we have used only 15 languages over here. And this is the figure size, and this is the bar plot. We have given the bar plot over here, and we have displayed the type of languages on the x-axis. So this is the x label and this is the y label. As you can see where we have count over here, and the size of the particular labels are mentioned in the font size. And over here we have given the x6 labels rotation is equal to 90. So what this does is that it inverts the uh, language name over here. As you can see, this is what the rotation does, and this is our plt.show. So this is the visualized bar plot, and over here this is our another visualization where we have used the value underscore counts on the director name. We have selected around 20 director names. Again, we have given the dark grid over here, which is nothing but our background, and this is the figure size 15,8, and we have used the bar plot over here. Again, we have given count on y-axis with font size 14, and name of the director on the x-axis or the x label with the font size of 28. And again, we have rotated the labels present on the x labels using the rotation is equal to 90. And this is our visualized bar plot. As you can see, the director's name, which is Steven Spielberg, repeats for the highest. It has a higher count, and followed by another director whose name is Woody Allen, followed by Martin Scorsese, followed by Clint Eastwood. So these are all the name of directors. And next visualization over here, we have taken a country on the x-axis and the IMDb score on y. So these are all the country names, and their IMDb scores have been mentioned on the y-axis over here. And as you can see, these are all the countries. And as you can see over here, again we have used the x-axis rotation is equal to 90, and that has rotated our labels. And so these are all the countries on the x-axis, and we have taken the IMDb score on y. And in this plot, we can see that the highest IMDb score is around 8.5, and this is the highest score. A country which received this score is called as Kyrgyzstan. And let us go ahead with our next visualization. And as you can see over here, in this visualization, we have taken the content rating on x-axis and its respective IMDb score on y. And this visualization also has a key over here, where the blue color represents a color movie, and the orange represents a black and white movie over here. And these are all the content ratings, PG-13, parental guidance, and all these ratings are mentioned on the x-axis. And again, let us go ahead with our next visualization. And over here we have taken content rating and its aspect ratio on y-axis. Again, we have used the same key again. Blue color stands for color movies, and orange stands for black and white. And in our next visualization, we have taken aspect ratio on x, and we have taken the IMDb score on y. And what we have done next is that there were a few null values present in our data frame. So instead of treating those null values, we have directly dropped those null values using the drop NA function. So using this function, wherever there are null values present in our data set, this function will directly drop such null values. And then again, we have checked if there are any null values present in our data using the df.isNull.sum. And as you can see over here, there are no null values. Previously, we had a lot of null values present in the entire data, and using the drop NA function, now there are no null values. So 0 means there are no missing values. And then again, we have displayed the column names, and wherever we found a particular column which is not of any use, we have dropped such columns as well. So the dropped columns include the movie IMDb link. So we have no use of this particular column. And for this data set, for this uh, drop function, we have also included the color and movie title, and we have also dropped the face number in poster, plot keywords, actor name, and the movie link, and the aspect ratio and language. These columns can be changed and experimented in order to see if there is any accuracy improvement or not. So for now, we have dropped these columns, and this is the resulting column now. This is the resulting data frame. And now, previously we had 28 columns. Now we have dropped 8 columns, and now the resulting data frame after removing the null values as well as the columns is nothing but 3756 rows and 20 columns. As you can see here, we have used the df.shape, and now the columns have been reduced to 20 in number. The next thing that we have done over here, what we have done over here is we have done label encoding. So as I told earlier, label encoder will convert all the categorical data into numeric, and we have selected columns like content rating, director name, genre, and actor 1 name, actor 2 name, and country. And we have applied label encoder on those columns. And now if we check the director name, so previously it was of object type, and now after label encoding, now the director name is of integer type now. And all the columns in our data belong to integer types or float types now. Now what we have done next is that we have applied a distribution plot. And what a distribution plot does is that it will show us the distribution of our data and tell us if our data is skewed or it's normally distributed. So we do it with the help of visualization. And as you can see here, these are the total number of rows and columns. We have given 4 rows and 5 columns. And the n rows are rows and n calls are calls. And the figure size we have given is 20, 20 over here. And we have given an index as 0. So it will begin from the starting of the columns present in the data set. And this is a tight layout that we have given. And as you can see over here, there is skewness in our data. This skewness can be seen over here. So there are a few columns like the actor one, Facebook likes, and gross, which are skewed. And this skewness has to be fixed. And we do it with the help of log transformation. So using the log transformation, we try to convert the data or transform the data into normal distribution and reduce the skewness. And as you can see here, we have selected the column names again, and these are all the column names, and we have saved these columns. So basically we have copy pasted this same column names in another cell, and we have put them in a list, and we have given these list name as skewed features. And the next thing that we have done is uh, we have applied the log transformation on the skewed features. So the entire data has been log transformed, and after the log transformation, this is the resulting distribution plot. So as you can see now, the skewness has been reduced and the data has been distributed uh, better as compared to before. So the skewness has been removed. As you can see, when it comes to director name, previously it was this way, and after applying log transformation, the distribution plot has completely changed now. So basically we have tried to change our data into a normal distribution, as you can see over here in this plot. And the next thing that we have done over here is we have split our data into independent and dependent columns. So as we know that the IMDB score is our target column, we have dropped it from X, and the X now has all the independent column, whereas the Y has the target column or the dependent column. And we have visualized the we have displayed the X dot head now. So as you can see, these are all the independent column names, and it does not have the IMDB ratings. But whereas when it comes to Y, we have displayed the head. Y dot head will display only the top 5 rows in that particular column, and this is the target column over here. These are the IMDB scores. The next thing that we have done over here is we have split our data into training and testing parts, as we had imported train test split previously. So here this code is related to that import. So what we have done over here is we have turned the data into X train, X test, Y train and Y test, and then we have given the train test split, and we have given the independent and dependent columns over here. Over here you can see that we have given a test size called as we have mentioned 0.2 over here. So what this does is that it will divide our data into 20% test size. It will give a test size of 20%, and the train data is going to have a size of 80% over here. So if we change the value from 0.2 to 0.3, then the train data will have around 70% of the entire data, and 30% of the data will be used for testing purpose. And then over here we have given a random state which is 40. So let's say among 5 people, 2 people use the same random state, then they both are going to get similar results. And then we have printed the X train shape, X test shape, Y train shape, and Y test shape. And these are all the shapes of the X train, X test, and Y train, Y test, and Y test. And the next thing that we have done over here is that we have applied machine learning models. So among all the models, the first model is our linear regression model. And over here you can see that we have used the linear regression, and we have done the linear regression dot fit on X train and Y train. And then we have used the model.predict on xtrain, which is nothing but the lm.predict. So basically our linear regression is in lm, and we have done the lm.predict on xtrain, and then we have also done the lm.predict on xtest. And in order to evaluate the performance of this model, we have used evaluation metrics in order to see how well this model has performed. And the evaluation metrics that we have used over here is the root mean squared error. So what we have done is that we have just applied mean squared error on y-test and test spread, which has the prediction on x train, and which has the prediction on x test. And then we have square rooted it using the np.sqrt. So we will get the RMSE, which is nothing but the root mean squared error. And then we have used the RMSE on the train data as well. Uh, we have used the same code again. We have used the np dot square root on mean squared error of y train and test spread. And over here we have printed the root mean squared error on training data, as well as the root mean squared error on the test data. And then over here you see that we have used a print command over here. So what this line does is that it will create a dotted line which will repeat for 50 number of times, and this is nothing but that dotted line. And then again, in order to see the r squared value, as I told earlier, the root mean squared error should be less, and the r squared value on the data must be higher. So the closer to 100, the better the model, and the RMSE, the lower or closer to 0, the better the model. And as you can see, we have printed the r squared value on x train, y train, and r squared value on test and train has been printed over here. And over here the RMSE is 12, as well as the RMSE on test data is 11. But as you can see over here, the r squared value on train is 40, and the r squared value on test is again 40. So this r squared value must be improved, and we have to basically increase the r squared value. And so far this model is not very good. But next thing that we have done over here is we have used the mean absolute percentage error to see the accuracy, and we have created errors, and we have subtracted the test predictions minus the y test, and then we have multiplied 100 on the errors divided by y test. So in the end we have the mean absolute percentage error over here, which is 95.5%. But as you can see, again we have to increase the r squared value as well. Let us use another model, which is the decision tree regressor. And over here we have used the decision tree regressor, and I have given a parameter over here which is the max depth. I gave the max depth equal to 9, and then we have used the decision tree and fit the decision tree model on x train and y train. And then these are the predictions. We have predicted the decision tree on x train, and then we predicted the decision tree on x test. And in order to evaluate this model, we used the root mean squared error again, as well as the r squared value, and we used the mean squared error and used np dot square root on it. And these are the y train and train predictions or train preds. And then we printed the RMSE on training data and RMSE on test data. Then we divided this root mean squared error and r squared value with this print command over here, drawing a dotted line. And this is the r squared value, and this is the r squared value on train, and then we printed the r squared value on test as well. Over here, as you can see, we have a very low RMSE value, which is 0.08, and the RMSE on test data over here is 0.12. But again, as you can see over here, the r squared value on train is 71, and the r squared value on test is 36. So again, this is not a very good model. But let us go ahead and print the mean absolute percentage error. And as you can see over here, the mean absolute percentage error After calculating, we found an accuracy which is 95.52. So let's go again and try other models as well. We have the random forest regressor, and the previous model, which is our linear regression, gave us a accuracy which is 95.5, and over here we have 95.52. Okay, and then we used our random forest regressor, and the same thing has been repeated. We use the random forest regressor dot fit on X train and Y train, and then we predicted the random forest model on X train, and then we predicted the random forest model on X test. Then we printed the RMSE value on train and test data, and then we splitted the evaluation metrics with the help of this line over here by drawing 50 dotted lines. And then we have the R squared value on train and test as well. Over here again the RMSE on train data is very less, which is 0.04. But when it comes to the RMSE on train data, again we have 0.10 over here. But when it comes to the R squared value, we can see that this model has performed very well compared to linear regression and the decision tree regressor. Uh, as you can see over here, the R squared value on train is 93 and R squared value on test is 56. So this is a very good model so far. And we have calculated the accuracy again with the help of mean absolute percentage error. And as you can see over here, we have an accuracy of 96.26%. And this model has performed very well compared to the previous models. So let us go ahead and use other models as well. So we have our k nearest neighbors regressor. As you can see over here, we have predicted this KNN model on X train and Y train. Again, same thing has been repeated. We have predicted the model on X train as well as X test. And in order to evaluate this model, we have used the RMSE score or the root mean squared error value, and then we have separated with this printed print 50 lines dot. We have divided the RMSE train and R squared value, and then we have the R squared value on X train, Y train. So basically we have predicted the R squared value on train and test. Over here you can see that the RMSE on training data is 0.10 and RMSE on test data is 0.13. And again our R squared value is not very good. We have a lower R squared value on train and test, and this model is performing very bad. And so far we will stick to the random forest regressor model, which has performed very well. And again we have used we have used more machine learning algorithms like the lasso, ridge, and elastic net. And again we found that the lasso model also gave us a very low R squared value. And as you can see over here, the RMSE is 0.12 on train and the RMSE on test is 0.11. Again, the R squared value is very less. And this is our ridge regression. Again, we use the ridge regression and we fit the model on X train, Y train, and we printed the RMSE on train and test data, as well as we have printed the R squared value on train and test. And over here again, the RMSE value is very low throughout all the models that we have used so far. The only problem is the R squared value. The R squared value is lower. And this is the elastic net model. Again, same thing has been repeated over here. We have used the model on X train, Y train, then predicted the RMSE values as well as the R squared values. And as you can see over here, again we have a lower RMSE value on train and test, which is 0.12 and 0.11. But when it comes to the R squared value, the R squared value on train is 0.39 and the R squared value on test is 0.40. So far random forest model or the random forest regressor is on top. And in the end we have used one last model, which is called as the XG boost regressor. And we have used this XGBoost regressor on X-train, Y-train, and then we printed the RMSE values on train and test, as well as we have printed the R squared value on train and test. And as you can see over here, we have a very low RMSE value, which is 0.01 on training data and 0.09 on test data. But when it comes to the R squared value, we have a very good R squared value for now, which says that the R squared value on train is 0.98 and the R squared value on test is 0.61. And we calculated the accuracy using the mean absolute percentage error. And as you can see over here, the accuracy is 96.49%. And when we compare this to the random forest regressor model, over here we have the accuracy as 96.49. And when it comes to the random forest regressor, the accuracy is 96.26%. So there is a slight change when it comes to the XGBoost regressor. But so far we can say, uh, when we compare these models with their R squared values, the R squared value over here in XGBoost regressor is 61 on test data. But when it comes to the random forest regressor, we can see that the RMSE, the R squared value on test is 56. So we can clearly say that the XGBoost regressor has performed very well when compared to the random forest regressor. So even the random forest regressor has performed very well, but we can say that the accuracy over here is a little bit higher as compared to the random forest regressor. And this model can be used in order to predict the IMDB score ratings. And the model can be further improved with the help of hyperparameter tuning. And we can tune the hyperparameters of the XGBoost regressor and the random forest regressor as well, and see if there is any increase in the accuracy of these two models. But for now, this is it for this video. Hope you like this video, and until then, have a good day, and I'll see you soon in the next video.